Okay, so seems to work. Great. Yeah, first let me thank the organizers of this conference and also of the session for inviting me here. It's a pleasure to be here. I really enjoyed the workshop so far, and yeah, thanks also to the audience that you are still here on Friday afternoon with the sunny weather. Okay, so yeah, the title of the talk is Geometry of Policy Improvement. Policy improvement means, well, the setting is the following. So we are in the setting of either a Markov decision process or a partially observed Markov decision process. So let me briefly recall you what I mean. So we've seen these kind of graphs before. So a Markov decision process would be you have some world state, and there's an agent who chooses an action, so a robot that reacts to the world. And then the action influences the world, but the world state at t+1 is of course also a function of the world state at t, so they both act together. And as we've seen before, so usually the agent cannot observe the complete world, so the agent has to rely on a certain set of sensors. So the sensors are denoted by ST. They depend on the world state WT, usually in a probabilistic way. So this is a Markov transition. Then the agent here chooses its policy. So depending on the sensor input, it chooses an action, and then the action influences the world, and then we continue. So yeah, this is a partially observed Markov decision process, or POMDP. And at the end of the day, the agent is interested in some reward function, and the reward, the idea is that you obtain a reward at each time step, and it depends on the world state and the action that you chose. Yeah, so maybe each action comes with a cost, and you want to control the system to move into certain world states where you can where you get a good reward. And then the only thing that the agent can control in this situation is the policy pi. And we make some simplifications here. So we don't assume that there's any memory in the agent. There are certain ways of incorporating this into this picture. So you could say that memories may be part of the world and then part of the sensor. So that's an easy way to incorporate memory into the picture, but of course that leaves then you have fixed the kind of memory and the implications of the memory. So that's and it's not that and there are other questions like if an agent has a limited amount of memory, how does he optimally use that? But that's a question I don't want to discuss here. And the other thing that's implicit here is that we are interested in stationary policies. So the agent has a certain fixed policy, and he never changes it. Okay, he does change it, but at least when we compute the reward, when we evaluate the reward, we don't incorporate the fact that the agent has to, at some point, or might learn or otherwise adjust his policy. Okay, so there's a natural way of visualizing such MDPs or POMDPs. So this is kind of a state machine. So the world, here the world it's a very simple world, it's a binary world. There are two possible states. There's a state A and there's a state B. And there are two actions, 1 and 2. If the agent, so suppose we start in A, if the agent uses action 1, the world moves to state B, but if the agent chooses action 2, then it can always stay in state A, so nothing happens. And in B, every action will bring the world back to state A, but but here it turns out that that maybe one of these actions has a high reward and the other has a low reward. So I've drawn here the 2 with a green color. Maybe that's the high reward. That's the good action to choose, and 1 is the not so good penalized action. Okay, so optimally, what would the agent try to do? Well, if you're in state A, you would like to choose action 1, go to B, and then get the reward by afterwards choosing action 2. And so you have to alternate between action 1 and action 2. Now there's a difference. If you can observe the world state, then it's very easy what to do. But if you cannot observe the world state, so if you don't know whether you're in A or B, so that would be the completely blind case where the sensor would tell you nothing about the world. So if you don't know whether you're in A or B, then the only thing to do is you can play 1 or 2 randomly. So depending on the value of the reward function, it might be advantageous to play 1 and 2 randomly, because then there's a chance that at some point you will be at 1, at some point you will be at A. There's a certain probability that you choose 1, end up here, and then there's a certain probability to have the 2 in the second state. This also illustrates what you can gain if you have memory, because if you have memory, you can play 2 for a while until you're sure to end up to be in state A, and then you always alternate between 1 and 2. For this you need memory, so you need to remember that the last time when you played 1, you played 2. So in this sense, I mean, memory is very natural to incorporate, so to not have memory is a strong restriction. But as I said, if you have limited memory or if you're fixed in the way you use it, then you can always model it as a POMDP. And so even though this is a very easy example, so the same phenomena will also appear more generally in more complicated examples. Okay, so that's another example. It's another simple example. There are again only 2 states and 2 actions, but here also action 1 means you stay at state A, and action 2 means with the probability 1 minus epsilon you always stay in A, but with the probability of epsilon you move to state B. But once you've reached state B, you will stay there forever. Okay, so this is qualitatively very different because I mean this has an absorbing state at world state B. So once you're at B, you can never leave it, no matter which policy you choose. Okay, so I will not. I will come back to this example later. But now, okay, so now I mean here in example 1, it was very easy to analyze this example even without telling you which function precisely I optimize. But if you're interested in long-term reward, then there are 2 natural possibilities. So one is the discounted reward. So the agent is, of course, interested in its immediate reward, and I mean that's very easy to evaluate the immediate reward. So the more you know about the world state, then you can estimate the actions. But then, of course, you don't want to bring yourself into a bad situation. Like here, you want to think about whether you want to be at B. And so there's this discount factor, which says that I also incorporate what happens in the future, but kind of discounted. So I'm more interested in what happens now, and I'm also interested about the future, but in a way which is controlled by this parameter. So the future at t time steps away is weighed by a factor gamma to the t. It's kind of an exponential decay. Okay, and then what do I sum? Okay, so this is normalization factor. Then I take the probability, and then I look. So at time step t, when I start with a certain initial distribution mu, so everything depends on the initial distribution. So I need to know where I start, or I need to incorporate this knowledge. Then I have a certain probability distribution at time t, and then I sum over the expected reward at that time step t, and well, this expectation, it involves, of course, well, the starting distribution, also the policy which I have chosen. And so And then at that time step, I also need to sum over the policy. Where there's a fine, there's a fine distinction. So the policy in the POMDP, it's a kernel from S, from the sensor values to the actions, but of course I can multiply that with beta, and then I obtain the corresponding transition from the world state to the action. Okay, so the pi tilde is almost the same as the pi, but just to be very clear here, I gave it another symbol. Okay, so that's the discounted reward. And then I can also say that maybe I'm interested in infinitely long, in the infinitely long future, and then so what happens usually in a Markov chain, if you let it, when you let it run long enough, then at some point the distribution converges. So at some point you start seeing an invariant distribution. There are some technicalities. I mean, in principle, it may also appear that you start oscillating or having a period, but then you can average over the period, and you will still get some invariant limit distribution. So you can also use this to evaluate the reward. So you can ask, so if I implement a certain policy and I wait infinitely long, then I'm in equilibrium, so to say, what will be my expected reward in this situation? And that's the so-called average reward. So I take the invariant distribution, which depends again on the policy, and it might also depend on the initial state, on where I started, and then I average the reward. Okay, so these are the two reward functions, and now we want to optimize these reward functions with respect to the policy. So the agent tries to take an optimal policy. Yeah, sorry?
No. I thought you want to show the... So I continue on the backwards?
Yes. Okay, so as I said, here we restrict to memoryless and stationary policies, and of course we also neglect many other problems, practical problems. So in practice, usually, or very often, you have a system that needs to learn and needs to adapt its policy, and and it's also the question whether the robot maybe even knows these kernels alpha and beta. So in practice, you might have to estimate them and so on. But for our purposes, it's yeah. So here we first assume a very clean setting where everything is known. Okay, and the basic question is so how stochastic are optimal policies? And there's a difference between Markov decision processes and POMDPs. So as I've argued here in example 1, if you don't observe the world state, so if you're completely blind, then you need a stochastic policy in order to get some reward. So this is an example for a POMDP where you really need a stochastic policy. The situation is different for Markov decision processes. So for a Markov decision process, it is known that you can always choose a deterministic optimal policy. Okay, but the thing is, can we say something about how stochastic an optimal policy has to be? So in particular, so the idea should be that the more we know about the world state, the better we should know what to do. So the general philosophy is that if we know more about or if our sensors get better, then the optimal policy should become more deterministic. I don't, well, okay, so that's the general idea, so that's what we would like to prove, but before proving that, we need to make that precise in some way. Okay, so that's the, okay, if I throw this up, do I get it down again somehow? Ah, there's the, okay. Okay, so let's first study the reward functions from a mathematical viewpoint. Now I've told you that this example here is fundamentally different from example 1 because of this absorbing state here. And also things depend a bit on your policy. So for example, if you start in and you can also see here that the invariant limit distribution depends on really depends on your policy. So if your policy is, I always choose action 1, then if I wait infinitely long, okay, nothing happens anyway. So your invariant distribution will always be you stay where you are. But even if you have a very small probability of choosing action 2 every now and then if you wait sufficiently long, you will be in state B with a very high probability, and in the limit you will. So the limit distribution is just the point measure on the world state B. So such a system is bad for several reasons. So it's natural to exclude them. So we had a technical assumption. Namely, we require that for all pi, so for any policy, the world state Markov chain is irreducible and aperiodic. Okay, I don't want to explain this, well, formally. If you don't know this, I hope that most of you have heard this, but the basic idea is that, so okay, a Markov chain is irreducible if you can reach any point from any other point with a finite probability. So if your policy here, okay, so here it is, yeah. So here it is satisfied if no, here it is not satisfied because you cannot get from B to A and not from A to B if the probability of the action 2 becomes 0, and this we want for all pi. So because so reducible Markov chain here. So if we cut this edge, then really, I mean, we have two different systems. We have the world A and the world B, and they do not interact in any way. And this we don't want. So this doesn't happen in example 1. So even if we put the so even if we give the edge 1 the weight 0, so if we always choose action 2, then we will always stay in A, but but even if we start in B, so it's not that we cut the Markov chain into 2. And aperiodic is related to the fact that you can have certain oscillations in your system, and they also make the analysis a bit complicated, so we exclude them for now. But the main technical consequences. The limit distribution well, it exists, it's unique, and it's independent of mu, and it depends continuously on the policy pi. Right, so we've seen in example 2 that this is not the case. If I change the pi, the limit distribution may change, may jump. And the second important thing is that the distribution of the world state converges to the invariant distribution. And of course, if you have oscillations, then this wouldn't be the case. Then we would have to average over the period in some way. Okay, so that's the nice technical properties. And what's the consequences? Okay. If you have this assumption, then the average reward is continuous as a function of pi. And that's important because if it's not continuous, then how do we know even that there's a maximum, so that there's an optimum, that we can find an optimal strategy? And one can even show that this can happen. So if you have example 2, maybe later I can show you that well, it may happen that the optimal strategy doesn't exist. So this is a bit better in the discounted case. Namely, this is always continuous. I mean, that's not so difficult to see if you look at this formula, but the reason why this average reward can become discontinuous is that the stationary distribution may not depend continuously on pi. Okay, so you can always optimize this, and so the discounted reward, but for the average reward, you need to check whether it's at all whether it's at all possible. Okay, then there's also a relation between the two reward functions. So as I already said, that well, the average reward is if you look at very long time scales. So this corresponds to the limit gamma to 1. And indeed, you can show that that this converges, that you have this convergence. And actually, you don't really need assumption star, but if you add assumption star, so the crucial point, what happens when you add assumption star, you have uniform convergence. Which means that you can, that for every epsilon, if you choose the gamma large enough, then the difference between the left and the right hand side here will be less than epsilon for all pi. Right? So that's uniform convergence. So you don't need to adjust the approximation level on the pi. But as I said, if you drop the assumption star, then you still have the pointwise convergence. And if you remember back to your early calculus classes, then it's one of the first things you learn is that if you have a pointwise limit of continuous functions, it need not be continuous. But if you have uniform convergence, then this works out. So the uniform limit of continuous functions is a continuous function. So here everything fits together, and you also have call it a theorem, but it's really a corollary from this and what you learned in your calculus class, namely that the limit, okay, I should say what kind of limit this is, that the limit of the maximum is the maximum and even more is true, I will not write it down, but if you have a sequence of maximizers here, so if you have a sequence of optimal policies, they will depend on gamma, and if you take a limit point, so if, for example, if they converge, if you have a convergent sequence of optimal policies, then the limit will also be an optimal policy for the average case. Okay, and that's basically an exercise coming from this result here. Okay. Okay, so that was kind of the topological part. So pointwise convergence versus uniform convergence. Now I still have half an hour for showing you some geometry. But first, let me explain you the main result. And this addresses the question above. So how stochastic does an optimal policy have to be? So in any POMDP, there is an optimal strategy pi star for gamma mu with support of so this is the support of the action policy given a certain sensor value. So it's the set of actions I consider. So the agent sees a certain sensor value, and then he says, okay, now I have 3 possible actions which I have to perform with certain probabilities, for example. And this is always bounded from above by the support of this function, which now is well, I mean, now things seem to go in the wrong direction. But this is nothing as, so if you see a certain sensor value, you can think about how many world states are compatible with this sensor value. Okay, so if I believe that there are 3 possible world states compatible with my sensor value, then I can fix a deterministic. Well, then there's an optimal policy such that I need to choose from at most 3 possible actions. Okay, so that's very nice. Well, that's a nice formalization of the fact that, or well, not the fact, but of the idea that the more you know, the more you know what you need to know. And under assumption star, the same is true for the average reward, which again follows from this. Well, I mean, follows from this other theorem. Right? Okay, I should also remark that that this is an extension of a. Okay, so this is a result I obtained with.
Could you give an idea of what the thing happens? Because in principle, like these 2 things like look like independent. Like states generated input. So what's the connection between these things that allows you to prove such things?
Yeah, so I will sketch the proof of this. But one thing which is quite interesting, it is not the case that, okay, so if I know that the world states are A, B, C, and suppose that in world state A, the optimal action would be 1, in world state B, the optimal action would be 2, and in world state C, the optimal action would be 1, 2, 3, then it can still happen that the optimal policy involves actions which are completely different. So what does not work is that you try to construct an optimal strategy based on an optimal strategy for the POMDP from optimal strategy of the Markov decision processes. So the fact that you don't know what's going on may force you to do different things, and we'll see an example of this also later. Okay, and the way to prove this, that's what I call the geometry of policy improvement. And it goes as follows. There's the problem in analyzing the discounted reward is that things are, in a sense, nonlinear because of the presence of this iterated distribution of the distribution of the world state at time t. So then you apply the policy several times and things get, in a sense, nonlinear. But on the other hand, what you gain is a certain iterative structure, and that's the so-called Bellman equation. Okay. And the Bellman equation involves the so-called state value function, which is basically the value that you would attribute to being in a certain state W. So suppose you're in a certain state W and you fixed your policy pi, then the state has a certain value, namely that's the expected reward you expect. It's the reward you expect when you are in this state, and it satisfies the recursion. This recursion. So basically, the expected reward or the reward you expect in a state W, it depends. Well, I mean, first there's the contribution from the present. So whatever action I choose, I get the corresponding reward. But then I also add a discount for the future. So at the next time step, I will be in a state W prime with certain probabilities, and then this new state W prime will also have an expected value, and I discount it with the factor gamma. And you can also write it as a sum for all t's of an expected value of the reward of the discounted expected reward you expect for all time steps. And it's also convenient to call this here the state action value function. So that's the value I expect when I am in state W, and I've already decided to go for the action A. Then there's the policy improvement lemma. Okay, so now the question is, how do you compare, or how do you decide how do you analyze what happens when you change the policy pi? And that's where the policy improvement helps. So suppose I have two policies pi and pi prime, and then I define, that's a bit technical. Okay, you can see that. Well, okay. So this compares the two policies pi and pi prime, and here you see the state value function popping up. And then one can show, if one plugs this into the Bellman equation, that this is the expected value of, if you start at, okay, if you use policy pi prime, and if you start at W, now there's again a discounted sum. And then this epsilon of W of t. Okay, so that's a bit technical, so it's not so important to analyze it on all points, but the relevant so why is it, how can you use it to improve your policy? Well, if all of the epsilons are non-negative, then this is a sum of positive terms. And then what one can do is one can just collect all terms that involve the omega here. So this is this is just the sum over all probabilities here that you are back in state omega, in state W. Sorry. So here I collect all of the terms W, and now at least at time step 0, I know that I am in W. So that's why this here is bigger than, or at least it's at least 1. Okay, and that was what we wanted to find. So we wanted to find, or what we want to find a policy pi prime, which which improves upon the policy pi. Okay, so that's so the 0 here is what we want. But actually, would be interested in having a strictly larger epsilon. But at least it tells us that So this gives us an idea of how to find policies which improve. Okay, now I need to think what to clean. Yeah, maybe the. Okay, any questions? Okay, so the idea is, okay, so the policy improvement lemma is a bit technical, at least in the statement. Okay, so actually I have to admit that I wanted to have the Yeah. I forgot to look up the reference. So this is an that, sorry?
Does the lemma say that if epsilon is true, then you can input?
Right. So if we succeed to find a pi prime such that epsilon is bigger than 0, then
yeah, but that's more or less like constructed. But how do you ensure that there is always a pi prime such that you can choose epsilon?
yes, I will show that. Okay, so the construction to find a pi prime is as follows. So the basic observation is that this condition that epsilon is bigger than 0 is linear in the policy. So first we define the following linear functions. So it's takes an action and maps it to a real number. No, it takes a distribution of the set of actions. So and then basically, and what one sees is that this is really something linear so that this definition of epsilon is linear in the policy, and that you need to and that this defines you a cone, so to say. So the policy improvement cone at a certain sensor state is pi s is the set of distributions over actions such that L pi w of Q is bounded from below by L pi W of the policy that you started with, given your or of what your current policy recommends you to do at a certain sensor state. And we only need to do this for those world states with a positive probability, so to say. So we don't need to do this for those world states which cannot appear in the when we know the sensor state. Then we also have so this is a cone. So it is defined by linear inequalities or by affine inequalities. And we have this for each sensor value. So it's a cone in the set of probability distributions on actions, and it depends on the sensor value. And now we put things together. So the total policy improvement cone is then it's now the set of policies. So it's the set of conditional distributions of an action given a certain sensor state, so that such that the policy for each given sensor state belongs to this corresponding cone. And so there, I mean, okay, so we've seen before that, so this is a set of stochastic matrices. And the set of stochastic matrices is a product of probability simplices. And in each of these factors of the product, we have one cone, and we combine them to a total cone. And one thing to note is that this cone is never empty, because basically the original policy always is in there. So that's good. But the question is, how big is it? So does it contain more than 1 point? So can we really improve it? Before I answer this question, okay, I think I will not answer that question in detail, but I will write down another lemma, which is maybe the policy improvement cone lemma. Namely, so which just formalizes, well, I mean, it just puts this construction into the other lemma, into the policy improvement lemma. Namely, if pi prime is in L of prime, then, yeah. Then we really have an improvement of the state value function, and we have this for all world states, for all possible world states. And okay, now this analysis so far, it just turned around the state value function for v pi of w, which kind of describes the situation if you start in a given world state. If you're interested in the discounted reward starting with an arbitrary probability distribution, then you need to then you can find this as a linear combination of these world functions as a positive combination, as a convex combination, which implies that also this inequality here is preserved. So this policy improvement is not only on the level of this value function, state value function, but also on the level of the discounted reward. Okay, now let's look at some pictures. So that's the geometric part, so to say. It's a polyhedral geometric part. Okay, so that's a picture from Guido, from my co-author. That's, yeah. Okay, now okay, so that's a sketch. Okay, so that's suppose that you have a certain policy. So this large triangle is a probability simplex in which you want to. So it's one of the components of your policy which you want to adjust, and then you have different hyperplanes corresponding to the different possible world states. And so here, if you are, so for example, in this example, if you are in world state 2, then really you would like to go in this direction. If you are in world state 1, then really you would like to go in this direction. But as you can see here, there's always a region where you can, which is compatible with both world states. And now to prove this theorem, you need to show basically that this cone is always large enough to hit a point which has this required property. I will put it up later again. And what is also interesting is that we also have in this policy improvement lemma, where is it? Here. No, then it's here. Okay, no, yeah, this is the version I want to know. So the nice thing is that if you look closely at this lemma, then this here, then this epsilon here, it's linear in pi prime minus pi, and so you also have a linear lower bound on your policy improvement. And And this is visualized here. So this from an actual computed example. So here this is the average reward. This is the value function. And if you start at a point here, then this is your cone, and this is the lower linear bound. And you can also see that this lower linear bound, or you can estimate that this lower linear bound is only valid in this cone. So if you extend this linear function outside of this cone, then at some point you will hit this surface. But within this cone, you really have a lower linear bound on this policy improvement. Okay, so basically, so that's okay. As I said, this is what this was actually computed from an example, and this is the example. So maybe that should be the last thing I explain. So the example has 4 states, and the system cannot distinguish, or the agent cannot distinguish states 2 and 3. From state 1, you always go to state 2 or 3 with probability 50-50. With action 3, you can move on to 4, but otherwise, so here from 2, you can stay at 2, or you can go to 3 with action 2. But here, if you chose action 2 here, then you will stay at action 3, and with the 1, you can return to 1. And the system is designed in such a way that the optimal thing to do would be, so if in the MDP case, the optimal thing to do would be to go from 1 to 2. The transition from 2 to 3 has a high reward, from 3 to 1 also has a high reward. But if you stay at 2 or if you stay at 3, then this gives you a negative, this incurs cost. Now, if you cannot distinguish 2 and 3, then there's no way of making use of this cycle. But then you have this additional pathway, so you can proceed on to number 4. And so in this example, we designed it in such a way that the transition, that action 3 here, actually it incurs a small cost of minus 0.1. But afterwards, all actions again give you a large reward. Okay, and this is, so the only thing which really matters, as you can see, is whether is what happens in state 2. So in state 4 and in state 1, the action doesn't have any implication, so the choice of the action doesn't make a difference, but but when we are in state 2 or 3, it does matter which action we choose. So the policy just belongs to this probability distributions over the actions, given that we are here in the middle. Now, suppose that I start in state 2. If I have a very low gamma, then the best thing to do is, well, I just think one step to the future, then I want to exploit the green, so the large reward from action 2 here. So which shows us that action 2 is optimal here. You can see it in this picture. If you think a little bit in the future, then things shift, and in the limit of gamma to 1, so in the average reward case, actually the optimal strategy is to always play choose action 3. As another example, if you start in state 3, then the optimal thing is use the action 1 to make use of this reward here. And again, in the limit of large gammas, then it doesn't matter where you actually started, so this picture actually is the same as on the previous slide. And here you can also see the policy improvement cones. And you can see that here for small gamma, actually, then the two recommendations are conflicting. If you start in state 2, then you would like to choose action 2. If you are in state 3, you would like to choose action 1. So the cone is very narrow. But it always points towards action 3. And that's the interesting thing. Action 3 is, in both cases, it's not, taken separately, it's not optimal. But the cones always take in this direction. Note that here at the boundaries, we also have the cases that if we are at these boundary policies, then the cone actually points towards the boundary of this simplex. So in this case, at these points, the policy improvement cone cannot be used to improve the policy. Okay, so I think it's time to stop. Thank you for listening. I also wanted to point to these two publications. So these are the results that I presented. So this is, okay, they are based on preliminary, or on not preliminary, but on earlier results due to Guido Nihat and Kian Ghazi Zahedi, who basically proved this theorem here in the case, just in those cases where the right-hand side here is equal to 1, so to say. And then, yeah, this is built on a refinement of the arguments and on a slightly better understanding. So yes, thank you for listening.
Are there questions?
About the geometry in your lemma, because it seems you get some open condition from nowhere, but in fact, what you do, I presume, is that you accept equalities, and you can go to the first of the same place.
Yes.
You don't augment, in some sense.
Yes.
You can go with equality until you find the smallest path.
Right. Right. So actually that's true. So I mean, so the theorem is also formulated in a careful way. So we say there is an optimal strategy. So sometimes, I mean, that also happens in the Markov decision process. Sometimes a stochastic policy is also okay, but the statement is that you can find a deterministic policy. And if you look at the cone, then what happens is that you can always move along the cone towards the boundary. And I mean, sometimes if you move along a face of the cone, then it means that that here this epsilon is 0. So you don't know if you strictly increase your reward or if you just stay at the same reward. But at least you can always move towards the boundary.
Thank you. Other questions?
I don't know if it makes sense, but do you ask yourself similar question in the case where you have several agents that can play different strategy, or and they all try to improve their reward and etc.
Okay, that's a difficult question. So I didn't ask myself that, but I mean, okay. So the general philosophy: the better you know what's going on, the better you know what you should do. I mean. That's a quite general philosophy, and you can ask yourself in which settings it is true. Now, once you have different agents, then things become complicated. I mean, then you're in the domain of game theory, and then it really depends on whether the task is to cooperate or whether you play against the other. So if you play together with someone, then most probably it is good to coordinate. So you should act deterministically, because then it is predictable what you do, and then your collaborator can adapt to it. Most probably. I mean, I didn't look into this. But if you play against an adversary, then sometimes it makes sense that to act unpredictably. So, for example, yeah, and because if you act predictably, then the other agent might react to it and exploit this. So in this sense, things are more complicated in that setting, and even the general philosophy may not be true. But you can, I mean, yeah.
Yeah, I was wondering this because in that case, there are some infield strategy solutions, and generally they don't necessarily match with the solution where you try to improve where every agent try to improve their reward at every moment. So I don't know, maybe it's something we can discuss after. I don't know.
Yeah.
Yeah.
So further questions? So I have a question. So usually when you consider hyperplane arrangements, so the number of regions increases first exponentially, but at some point it only increases polynomially. And many of the regions that you would expect do not appear anymore. So can it happen that you prove that it can't, but so what's the mechanism behind it? So in principle, at some point, it could be that you can't find a region which increases
yes.
for all world states.
Okay, basically, I mean, what kind of happens here is that if two world states are possible, then you have two hyperplanes. And then there's always one direction in which you can go. If you have three, so to reduce the cone to a point here, or at least generically, you need a third hyperplane. But that's also fine with the theorem. Well, I mean, then you cannot improve, but then the theorem tells you that you have to play a mixture of three policies, but every policy here is a mixture of three actions. So and it's this kind of dimension counting which I didn't present here, but which lies behind this theorem.
That was because here your hyperplane are linear because they always pass through a fixed point.
Yeah.
This is not a situation where you take a final.
No, it's not, but the same rule applies there. So at some point you don't get exponential, I mean, so it could happen that the region where you increase, yeah. Okay, let's thank Johannes again.